My name is Adam Groenwald. I'm the team lead. I work primarily on the concept, mechanical design, and control.
My name is Austin Lines, and I worked on the mechanical design of the shrew.
Hi, I'm Joshua Elliott. I worked on electrical design as well as modeling and simulation.
Hi, I'm Chris Like, and I worked on the connector arm subsystem and the mechanical design.
Hi, my name is Margot Jennifer, and I worked on the lunar design and the mechanical prototype.
Hi, my name is Grace Player, and I worked on the lunar design.
Hello, my name is Andrew Scow, and I worked on the lunar design and the mechanical prototype.
My name is Philip Mulford. I've been primarily working on winch and internal joint control and implementation.
Hi, I'm Laura Ray. I'm the faculty advisor for this team, and I'd like to thank NASA and the Big Idea organizers for their support.
We're the team from Dartmouth College, and we're proud to present to you our concept for exploration of the lunar South Pole.
We introduced Strategic Highly Compliant Roving Explorers of Other Worlds, or SHREWs, a mobility system for lengthy traverses into lunar permanently shadowed regions. SHREWs are low-cost, lightweight roving modules that can travel in a variety of locomotion modes. Our concept advances the ability to characterize subsurface water ice concentrations and characterize PSR stratigraphy in advance of crewed missions. This is done by directing our attention to the mobility platform the instrumentation is attached to, such that the four-wheeled, all-wheel drive units can effect their own extrication from immobilizing terrain. SHREWs employ a novel expanding midframe, which redirects tractive effort to the front or the rear of the rover as needed. Inspired by blind shrew pups, which link to form a caravan behind their mother as they travel across the forest floor, our shrews are also collaborative in nature, and are able to autonomously or semi-autonomously initiate the linking of units and proceed to travel as a collective. This provides system redundancy against immobilizing terrain and enables lengthy collaborative passages into the depths of craters. Our concept is an innovative robotic platform for characterizing PSRs through partially tethered ground traverses. The core innovations of this work are a low-mass alternative to the traditional rocker bogie suspension, a novel expanding midframe joint which enables push-pull type mobility and compact transport, and a linking mechanism which allows multiple vehicles to join together and travel as a group.
In the remainder of our presentation, we first explain the need for such a system. We then give a detailed discussion of the SHREW's design concept, which includes the concept of operations on the lunar surface, early validation of the concept through simulation, the Phase A detailed design of the terrestrial prototype, and concept design studies of the lunar vehicle. We then present prototype testing, and finally we summarize our project management, which includes the project lifecycle, timeline of our work, path to flight, safety protocols, and the budget of our work under this challenge. While NASA missions like the Lunar Crater Observation and Sensing Satellite or the Lunar Reconnaissance Orbiter have nearly universally shown the presence of water ice in lunar PSRs, these surveys are of relatively low resolution, with global maps limited to a pixel density of several meters. As we turn our attention to in situ resource utilization, or ISRU, we must further characterize the surface properties prior to a crewed arrival under Artemis 3 in 2024, such that study is focused locally and the crew is kept safe. This need lends itself to a mobile scout. Extreme temperature variations, limited access to solar energy, and communication constraints are the problems central to ground-based surveying. Moreover, immobilization in uncertain terrain conditions risks slowing scientific objectives, especially when traversing steep crater walls. Consequently, our team focuses on robust mobility, building on more than 15 years of expertise in designing rovers for extreme environments, to construct a lightweight, collaborative robotic mobility platform suited to access the unknowns of lunar craters and overcome the associated problems pertinent to ISRU.
We begin with a mission scenario illustrated in this animation. A commercial lunar payload services lander delivers 4 shrews 100 meters away from the PSR in their transport configuration. The modules exit the lander and expand to the driving configuration, beginning their approach to the crater rim as a caravan. Upon arrival at a peak of eternal sunlight, a higher battery capacity solar panel vehicle maintains its position on the rim to charge, while the remaining vehicles descend. A vehicle unspools a winch cable to lower itself and the other 2 vehicles up to 3,000 meters. A second vehicle unspools an additional 3,000 meters to deliver the final shrew to more level terrain. The winched modules serve as communication relays and can carry low-mass, passive instrumentation like Geiger counters. The final shrew detaches and begins to characterize the environment using a ground-penetrating radar and spectrometer. Upon completing its traverse, the solo vehicle reattaches. The ascent mirrors the descent, respooling from the bottom to avoid dragging the cable. At the top of the rim, the vehicles recharge and transmit data prior to beginning a new cycle. Site selection is informed by global maps derived from NASA LOLA and LCROSS data. The shrews will deploy to the rim of Shackleton Crater following the traverse cycle shown in green. The major objectives of the mission are to characterize subsurface stratigraphy for water ice and volatile distribution for in situ resource utilization. Additionally, bombardment processes, surface weathering, and the history of the inner solar system may be assessed by focusing on geological transition regions like the minor slump lobes at the base of the crater. Several existing vehicles informed our design process. Scarab is a 312-kilogram four-wheeled rover developed by NASA and Carnegie Mellon University designed to drill into the lunar surface. Its unique internal joint varies the wheelbase, enabling inchworm-like locomotion. This mobility mode is achieved by sequentially driving the front and rear wheels while expanding and contracting the internal joint. This inchworm movement allows the robot to escape terrain that would otherwise cause immobilization. NASA's Viper robot is designed to investigate volatiles near the lunar South Pole. Using multiple active degrees of freedom at each of four wheels, Viper is able to swim through sand by undulating its wheels in a coordinated manner. NASA's DoAxle is a four-wheeled rover for exploring steep Martian slopes and consists of a central body and two detachable tethered axles. When combined, the vehicle can cross moderate terrain to reach cliff edges, where the two axles detach with the body acting as an anchor. While these technologies informed our design process, none of them met the unique needs for scaling the steep slopes of permanently shadowed craters near the lunar South Pole.
Modeling and simulation is an important aspect of concept development that precedes detailed design and fabrication. We used Robot Operating System, or ROS, and Gazebo to model and assess mobility features of our Shrew concept. ROS is a software architecture that speeds up robotic software development, and Gazebo is a physics simulation environment for robotics. ROS and Gazebo combined allow robots to be tested in simulation before they exist physically. For Shrews, a number of aspects were validated in simulation. The inchworm motion, which was validated by the larger Scarab vehicle, was simulated for a 15-kilogram Shrew. By simulating the rigid body dynamics of the Shrew, we can develop and test control algorithms that would otherwise require iterative troubleshooting in hardware. An example of this is the tendency during push-pull movement for the front axle to turn into areas of lower traction. Knowing this allows us to develop control laws that can be transferred to actual hardware. The controller required for driving and steering multiple linked shrews was also developed through simulation. Simply steering the frontmost axle of the shrew caravan in the desired direction while keeping other axles straight results in jackknifing and immobilization. Instead, to properly steer a multi-shrew caravan, the frontmost axle points to the desired heading. Then, the front axle on each follower shrew is controlled to remain perpendicular to that shrew's linking arm. Lastly, each shrew's rear axle mirrors the angle between the front axle and body. This causes changes in the heading to propagate down the caravan of shrews from front to back. While the solution is simple, the simulation environment avoids extensive iterative physical testing or sophisticated mathematical modeling of the system dynamics and informs the shrew design.
Our team established design requirements based on extensive analysis, iteration of viable mission scenarios, and system needs illuminated in Gazebo. The challenge specifies a lunar system mass requirement below 15 kilograms, as determined by the CLPS landers, and cost. Additionally, we target low ground pressure to minimize sinkage in soft terrain. Naturally, limiting the mass of both the lunar and the terrestrial shrew is crucial. The length and volume of the compacted shrew must also be minimized to save space. Sensitive electronic components must be protected and maintained in a stable temperature range. Taking into account the power requirements derived from terrain resistance, a target speed, and the expected slopes of our ConOps, we established the viable range of traverses between charging cycles. Finally, the mid-frame joint must exert a minimum force in order to actuate the rover over small obstacles. Our detailed design follows from these system requirements. Mechanically, the robot consists of an axle linkage on each end to which drive motors, operational attachments, and scientific instrumentation are fixed. Between these is a gantry mid-frame linkage, to which a warm electronics box is mounted. The mid-frame contains a prismatic joint driven by an internal lead screw and a single brushless DC motor. The attachment points between each axle and the mid-frame contain a yaw degree of freedom limited to plus or minus 45 degrees, and a roll degree of freedom limited to plus or minus 30 degrees. Yaw alone enables the 5 distinct pose morphologies shown here, 2 for straight travel and 3 for turning, each impacting mobility with various benefits. Roll ensures compliance with the immediate terrain, much like a rocker bogie suspension, but with lower mass. Finally, the mid-frame allows for changes in the wheelbase. Drive motors are sized based on the loads anticipated while driving up a 15-degree slope continuously, when we're towing another vehicle intermittently, at a speed of half a meter per second on Earth, or 0.42 meters per second on the Moon. Locomotion on steeper slopes is aided by a winch. We assume rigid wheels on a plastic non-cohesive surface, and a rolling resistance of 30% of the normal force, following seminal papers in the literature. The required maximum continuous torque is 3.75 newton meters on Earth and 0.46 newton meters on the Moon. For the terrestrial prototype, we select an OEM 63-to-1 brushless gear motor, whereas the lunar version will use brushless motors and custom gearboxes sized for peak efficiency under the lunar loading condition.
We sized the mid-frame to support the electronics box, and the surfaces on either end of the vehicle allow for the mounting of a linking arm, a winch, and scientific instruments such as ground-penetrating radar, spectrometers, and cameras. The Earth prototype linking arm allows two shrews to connect and disconnect. When connected, the units function as a larger caravan with the ability to transfer power between each module. A rod linear actuator with potentiometer feedback allows the arm to extend to the other vehicle. Based on the mass of this actuator and the estimated mass of the end effector, 2 high-torque servo motors and 7-to-1 gearboxes were selected to control the arm's pitch and yaw movement. The end effector plug features a custom aluminum mount and a ball joint linkage that allows the plug to rotate when it's not perfectly aligned. An aluminum plate is attached to the ball joint linkage and serves as the strengthened backing to the 3D printed spring-loaded plug. In order to transfer power, the plug has copper bus bars that protrude out of the plastic in a radially symmetric pattern, similar to a coaxial power connector. Embedded springs in the plug push the bus bars against the envelope receptacle to make the electrical connection. The rest of the envelope is fabricated from aluminum sheet metal and acts as a funnel for the linking end effector.
Incorporating a winch into the shrew's design allows control over the rover's descent down the steep crater walls and preserves onboard energy of the lowered shrew. Also, the winch supplements wheel motor torque when climbing out of the crater to keep these motors optimized for lower angle terrain. Due to the distances between the rim of the crater and the regions of scientific interest, the winch cable must be at least 6 kilometers long. The cable acts only as a structural element since data or power transmission add significant weight and volume. For the lunar design, we selected Kevlar thread, 3 kilometers in length and less than half a millimeter in diameter, due to its high strength-to-weight ratio, good abrasion resistance, and its capability to withstand the extreme temperatures and UV exposure on the moon. This also dictated that a level wind be added to the design to manage the spooling of this extensive length.
Shrews can carry a payload of scientific instruments from 1 to 5 kilograms mounted on the midframe or top either axle. An existing miniaturized ground-penetrating radar unit optimized for lunar prospecting with TRL-4 could be implemented into our rover design to image the subsurface of the PSRs. This system, which weighs less than 1 kilogram, has a 5-meter penetration with 15-centimeter resolution. By utilizing the shrew's expanding chassis to separate the transmitter and receiver antennas, we could achieve an even greater penetration depth. RIMFAX, NASA's GPR on Perseverance, could also be reused for deployment via a shrew. This GPR has a mass under 3 kilograms, consumes 5 to 10 watts, and penetrates to a depth of 10 meters. A variant of Perseverance's Sherlock spectrometer can be carried to detect minerals and organic molecules. A PSR version could eliminate the imager to reduce power, mass, and size.
Each prototype operates on 2 microcontrollers equipped with IMUs and encoder channels to ensure wheel rotation as well as roll and yaw angles. The primary microcontroller provides direct control of the wheels through 2 motor controllers. The second microcontroller sends actuation commands to a midjoint and winch motor controller, as well as the level wind. Each microcontroller reads encoder channels for motor speed control. The primary microcontroller also commands a Raspberry Pi that controls the linking arm by locking onto a colored LED emitting from the target robot and extending the arm to make a connection. This is confirmed through the completion of a circuit between both robots. Each motor is controlled to maintain a commanded speed using proportional integral feedback control. 2 outer loops, one for each axle, set the commanded speed to each wheel speed controller to maintain a commanded yaw angle between each axle and the midframe. The outer loop increments the commanded motor speed of one wheel and decrements the opposing wheel through a simple proportional controller to maintain a commanded angle. This provides steering with minimal wheel scrub to accommodate terrain heterogeneity. Encountered obstacles cause the yaw angle of the passive joints to diverge from the reference angle, as shown in the figure. The system is tuned so that for large yaw angle errors, wheels on the same axle can move in opposite directions to allow the axle to repoint at slow speeds. Detecting yaw angle response also serves as an excellent proprioceptive sensor of terrain condition and heterogeneity.
The lunar concept follows directly from our Earth-based vehicle while considering the required changes for operation in the lunar environment. We consider dust mitigation, thermal protection, and size and mass reduction. Lunar specifications require the use of advanced materials, custom electronics, and scaling of the Earth rover. Payload-carrying shrews are not equipped with winch mechanisms and have a mass between 13.5 and 15.5 kilograms depending on the instrumentation. Shrews with winches and linking arms have a nominal mass of 15.3 kilograms. The motors and gearheads are scaled for lunar loads, and the wheels are narrower to maintain similar ground pressure to the terrestrial vehicle while reducing mass relative to the terrestrial prototype. The electronics box provides insulation for the thermal system. We propose a series of dust mitigation systems to protect vulnerable components. The midframe joint and motors are subject to dust disturbed by the wheels. The drive motors are housed in a sealed casing that leaves only a floating sealed bearing for the shaft to exit the box, sealed with PFPE grease. The midframe joint is encased in a continuous sleeve of layered beta cloth, a common material used in space applications, using the layer pattern shown here. The sleeve matches the maximum length of extension and is fairly tight around the joint to prevent bunching that could interfere with operation. These materials are known to resist contamination and trap smaller particulates, making them an effective barrier for this application. The linking arm frame will be protected with layers of beta cloth similar to the midframe joint. We present two mitigation solutions to protect the electrical connection face. The first places brushes designed for lunar solar panel cleaning on the end of the arm, which would sweep particulates from the surface as needed. The other potential solution leverages the charge of the particulates, employing an electric curtain to repel the charged dust from the surface. The winch drum and motors are housed in a sealed box, but the cable is prone to contamination. We propose a solution that places the same brushes as the linking arm system in an open-sided frame, preventing buildup of dust. The cable is drawn through the system before entering the box, preventing contamination of the interior mechanisms.
The primary considerations in selecting materials for the lunar rover are thermal and mass properties without compromising strength and performance. Nomex sandwich sheets form the lunar rover's front and rear axle frames. This material features a lightweight honeycomb Nomex core laminated between two thin fiberglass sheets that can be cut and folded into three-dimensional structures. We show that folded Nomex sheets offer viable strength for the rover frame through lab testing. Structural strength is the critical design factor for the lunar rover's midframe and linking arm. A carbon fiber frame houses the steel lead screw for the midframe, and carbon fiber and aluminum form the linking arm mechanism and V-envelope. These materials meet mass and temperature specifications while retaining the strength and rigidity of our terrestrial concept. Lunar temperature swings also require a motor lubricant that can function in extreme temperatures. We select a commercial lubricant that is a PFPE-PTFE mix often used in space applications for its wide temperature range and its low volatility and outgassing factors.
In order to ensure that the electronics operate within their temperature limits, the lunar design incorporates a warm electronics box, or web. The web contains a paraffin wax heatsink to store and dissipate thermal energy. Paraffin wax was selected for its low melting point and high heat diffusion at 230 kilojoules per kilogram. Our design utilizes a multi-layered insulation to limit the amount of heat transfer via conduction, shield the sensitive equipment from solar radiation, and limit the amount of heat radiated away by the system. Assuming that the electronics dissipate 8 watts of power as heat when being used, the computational model indicates that the electronics perpetually remain within their operating temperature range of -40 to 60 degrees Celsius. The web's outer layer serves to protect its contents from the harsh solar radiation during the lunar day and is made of a Nomex core with a white barium sulfate outer coating and a silver beryllium copper inner coating. The outer coating provides an extremely high emissivity and extremely low absorptance. The inner wall has a Nomex core and is coated in vapor-deposited titanium due to its lightweight and low emissivity. Lastly, thick layers of aerogel insulate the inner and outer boxes from each other and the outer box from the rover frame.
Robots entering a permanently shadowed lunar crater rapidly lose line of sight and radio contact with the lander parked near the rim. However, the Shrew Caravan provides a communication relay between the lander and the Shrew deepest in the PSR. The challenge specifications assumes 70 kilobits per second of bandwidth per kilogram of payload, or 1.05 megabits per second per 15 kilogram Shrew, which is sufficient to transmit low frame rate, low definition video. We envision human-assisted path planning coupled with robot autonomy using simultaneous localization and mapping, or SLAM, as a means of operating Shrews within PSRs. Communication bandwidth allows transmission of GPR data to Earth at a rate of 0.15 seconds per meter to assist travel with path planning for resource identification.
Physical testing of the terrestrial prototypes was focused on two primary factors. First, we aimed at demonstrating functionality of the novel aspects of our concept. Does the rover physically behave the way it was designed to? Second, although we performed a variety of simulations for operation in the lunar environment, creating realistic environmental test conditions, where possible given budget and travel constraints, provides a contextual metric aimed at advancing technology readiness level. These tests include locomotive performance testing, linking tests between two prototypes, flexural testing of lunar frame materials, and power and energy measurements. Locomotion testing is first performed in grass to set a baseline. Early tests show the rover heading drifts less than 1 degree per 10 meters when commanded to drive straight. Next, we assess the different vehicle poses to see if they behaved as expected. Here you can see the rover performing a symmetric left-hand turn with minimal scrubbing. Crab driving and the different turning configurations all behaved as expected, with a minimum turning radius of 75 centimeters. The prototype can climb a grass slope of up to 25 degrees, while mobility is limited on heavily vegetated slopes of 30 degrees. Sand was our low-cohesion simulated lunar terrain, for a cost-effective solution that would not violate travel constraints. Plastic inserts were added to wheels after realizing the slots between grousers results in undesirably high sinkage or high centering of the shrew. We find that this reduces sinkage to just 3 centimeters, which verifies ground pressure requirements previously established. The wheels with inserts allow the vehicle to traverse sand mounds of 25.5 centimeters high. as shown here. For reference, this mound is 91% of the wheel diameter. Benchtop testing verifies the actuation of the mid-frame joint through manual commands. Shown here is a full actuation sequence from the maximum wheelbase to the minimum allowable wheelbase. These tests show that the mechanism has merit and can be incorporated into locomotion modes in the future.
We tested the linking arm mechanism to verify that our two shrews can mechanically and electrically join when they aren't perfectly aligned. Here's the full linking procedure. Notice that the arm leaves the blue plastic stand and begins its sweep procedure looking for the tracking object. Once the tracking object is in view, the arm slowly centers itself above the envelope receptacle and the linear actuator extends out until it hits the back of the envelope. The arm then moves down into the envelope where the 12-volt electrical connection is made with the copper bus bars and the end effector plug. You can hear this with the buzzer. The shrew then cuts power to the servo motor so they have freedom of movement during driving. To verify that the shrews can link when they aren't perfectly aligned, as is likely under lunar operation, we performed a series of tests with them facing each other from various distances, angles, and relative heights. As you can see, the linking arm consistently located and moved toward the tracking object at varying positions, with the ball joint on the end effector fixing angle alignment differences. We also tested the shrews linking in total darkness, with the arm tracking a green LED rather than the colored disc. These tests verify that the shrews can autonomously connect when they are within 50 to 80 centimeters of each other, facing each other within 45 degrees, and have a height difference within 30 centimeters. The shrews link in a completely dark environment similar to that of a permanently shadowed region, and when linked, they transfer power. The results of these tests demonstrate that this technology has merit and can be adapted to the lunar environment.
To validate the potential for constructing the lunar vehicle frame from Nomex honeycomb panels, we performed flexural testing on box section structures made from 6mm thick sheets. These tests, performed following ASTM standards, provided validation of this material's structural strength. Force was applied vertically through the loading bars, with fixed support bars beneath the structure. Buffer blocks are placed over the support and loading rollers to distribute the pressure and prevent localized compression of the sheet's sandwich construction, and to instead test the yielding strength of the full beam. These tests proved that these composite beams would be of sufficient strength to resist the worst-case bending conditions the vehicle may encounter during the mission lifecycle.
The mission profile for the shrew that disconnects to explore the PSR comprises the upper bound on energy requirements. Our concept assumes that this vehicle reaches the lower crater with over 350 watt-hours of energy stored in the 500 watt-hour battery after winch-controlled descent of the crater wall. Energy measurements for our terrestrial prototype refine our design estimate of energy use for lunar missions. We measured the average and instantaneous drive power of our terrestrial prototypes over a short length of level sand as 64 to 69 watts, including 8 watts of housekeeping power. Excluding the housekeeping power results in a projected efficiency over sand of 27 kilometers per kilowatt hour at the speed shown here. We also measured energy directly for a 400-meter test on grass at 30 kilometers per kilowatt hour. Power estimates for a 15-kilogram lunar rover operating in lunar gravity include a revised housekeeping power for space-rated electronics, such as the IBM RAD 6000 processor, instrument power, and lower drive power for a total average power of 24 watts, with 16 watts total for housekeeping and instruments and 8 watts for driving. Given these estimates, a mission duration of 19 hours requires 322 watt-hours of energy. We sized the lunar rover battery for 500 watt-hours, providing 178 watt-hours, or 36% as energy reserve.
The COVID-19 pandemic resulted in completion of all mission development and design work remotely. Additionally, our full team was unable to access campus lab facilities due to the college's COVID-19 restrictions, so we completed implementation and testing in off-campus garage labs. Due to these restrictions and COVID-19 schedule setbacks, some physical testing still needs to be completed. This includes the testing of push-pull locomotion on sand using the mid-frame joint for an individual shrew, and collaborative motion testing for the 2 linked shrews. We are in a strong position to complete these tests in the coming months. Quantification of mobility characteristics should include drawbar pull test on GRC-1 lunar soil simulant. This could be done on both flat surfaces and on the adjustable tilt bed in the NASA Slope Lab. Further testing also remains for the winch system. These tests will quantify the max slope possible when winching a shrew up an incline. Work done prior to the Dartmouth team's 2020 Big Idea Challenge proposal serves as the first system lifecycle through pre-phase A. Acceptance as finalists and the feedback provides the preliminary key decision point, or KDP. In early March 2020, our team began Project Phase A, concept and technology development. The Dartmouth engineering team is near the end of Phase A work, having performed rigorous simulation of the mission scenario and assessment of prototype system performance. We intend to continue into mid-March under Phase A in response to the forum and paper review, acting as a formal mission definition review and secondary KDP. Pending a go indication from key stakeholders, our team intends to pursue Phase B financial support in early spring 2021. We classify the current shrew mobility concept as TRL-4, a low-fidelity system that is built and operated to demonstrate basic functionality in critical test environments. Critical software components are integrated and functionally validated. The mid-frame joint mechanism and shrew caravan concept are consistent with TRL-3. Analytical studies place the technology in an appropriate context, and lab demonstrations, modeling, and simulation validate analytical predictions.
Conceptual design of shrews began in November 2019. The team worked on the mission scenarios and a detailed concept design, which led to selection to the Big Idea Challenge in February 2020. In mid-March, Dartmouth announced COVID-19 closures, laboratory research shutdown, and remote work across the country commenced through the end of the summer. By late spring, with the mission scenario defined, we finalized design requirements and completed the detailed design for the midframe, winch, and linking mechanisms. Between spring and fall, we conducted ongoing design studies to assess additional requirements of the lunar prototype. During the summer, we constructed and assembled the terrestrial prototypes and developed the lunar concept, including dust mitigation and thermal system concepts. We completed the electronic systems, sensing, and software in the fall and performed the testing reported here. Development of our rover concept is on track to be deployed to the lunar surface prior to arrival of Artemis 3. Our project follows the phase cycles as defined in the NASA Systems Engineering Handbook. For Phase B, we will build a second version of our terrestrial prototype to increase the concept's technical specificity. We will prototype and test the worm electronics box and our dust mitigation concepts and increase the shrew's ground clearance. We will also integrate the winch with the linking arm, allowing the shrews to connect and disconnect from the winch cable for independent travel, as required by the mission scenario. In Phase C, the final lunar design can be implemented in collaboration with the Glenn Research Center and NASA JPL, and in Phase D, the rover will be tested, integrated with the mission, and deployed to the lunar surface.
Project development followed best practices regarding emergency escape plans, safety and training, and equipment specified by our institution. As it pertains to the COVID-19 pandemic, the team complied with guidelines set by Dartmouth College and the state of New Hampshire, including wearing masks, maintaining 6 feet between group members, and reduced occupancy in remote labs.
NASA supported $83,000 of the project costs, and we leveraged internal resources valued at over $100,000. A direct cost breakdown shows roughly 61% of NASA expenditures for payroll and roughly 31% to fabricated equipment. The remaining 8% of the budget covered indirect costs for the project at a reduced indirect cost rate. We initially proposed to demonstrate the functionality of a single rover by constructing one prototype unit. Despite the lowest budget of all the finalist teams, we pivoted to construct a second vehicle such that we could begin testing collaborative functions. This was made possible by shifting from our initial intent to construct a prototype from Nomex, which became infeasible under COVID-19 constraints, and by using low-cost verification methods. We believe that we have realized considerable value to NASA and industry partners on a modest budget.
Shrews offer a solution to the 2020 NASA Big Idea Challenge by providing capabilities to explore and operate in PSRs. Shrews are able to operate in friable terrain with the aid of the expanding and contracting midjoint and through the caravan concept. The midjoint provides locomotion modes that reduce risk of immobilization, while the winch generates sufficient force to pull a robot up a 25-degree slope. The linking arm allows independent or collaborative operation and conducts electrical energy across the arm connection, enabling power transmission and recharge of individual shrews. The design and testing of shrews provides innovations in mobility by enabling a rover to overcome unknown terrain conditions on its own and by creating a method for a team of robots to traverse previously impassable terrain, thus prolonging the length of missions in PSRs.
This work would have not been possible without the guidance of our team advisor, Dr. Laura Ray, Scott Ramsey, who machined parts for the team when we were unable to access facilities, and Ava Klein, who assisted in assembling the final presentation. We would also like to thank the National Institute of Aerospace, the Big Idea Challenge organizers, and the challenge judges for the opportunity to be involved in this work as students in the Artemis generation. Lastly, we invite the members of the public to view our poster, which is accessible via the Big Idea webpage, for more information about shrews. Thank you.